everyone, it's Dre here again to explain the Lewis relation for my part 1 of my exam 3. So I'm going to start off by writing out the Nusselt number as the heat transfer coefficient times a characteristic length d over the thermal conductivity k. And then we also have, in mass transfer terms, we derived the Sherwood number last time as the mass transfer coefficient times a characteristic length d over the diffusion coefficient dAB. And so what we defined before is the Sherwood number is equal to a coefficient A times the Reynolds number to the B times the Schmidt number to the C. And we could find out these constants by doing a mass transfer experiment. And you could determine these values for A, B, and C. And what's kind of interesting is if you were to actually do the same experiment with the same parameters, but in thermal parameters, looking more at temperatures, you would actually find that the Nusselt number has the same relationship as A times the Reynolds number to the B times the Prandtl number to the C. And you would find that these values are actually the exact same if you were to do experiments in the same manner. And so this is going to help us derive the Lewis relationship that we're looking for. So if you were to take the Nusselt number over the Sherwood number, you know that these are going to cancel out. So that basically is showing you that the velocity at which you're doing the experiment does not matter for this. So we know that the Prandtl number is equal to the kinematic viscosity over the thermal diffusivity, and we know that the Schmidt number is equal to the kinematic viscosity over the diffusion coefficient, dAB. And so we know that those are going to cancel out, and this is going to equal the diffusion coefficient over the thermal diffusivity. And so this is what is referred to as 1 over the Lewis number. And if we're looking at a system with moist air, we know, well, let me drive. So the thermal diffusivity can be rewritten as the density times the heat capacity over the thermal conductivity. And we're going to throw in our diffusion coefficient. And so if we have that as 1 over the Lewis number, for moist air, the numbers for each of these is going to actually end up equaling about 1. So we know that the Lewis number relation for this is going to be 1. And this is going to be important going forward, but we're going to rewrite this again. The Nusselt number over the Sherwood number is equal to, and we're going to look more at this side of the equation now. And so again, we see that the characteristic length or the diameter, whatever the size of your experiment, is not going to matter. So that cancels out, and we're left with the heat transfer coefficient over the thermal conductivity times the diffusion coefficient over the mass transfer coefficient. And what we want to derive is a relationship for the heat transfer coefficient over the mass transfer coefficient. Again, on the right side of the equation, we have our Prandtl number over our Schmidt number to the C, which we found is 1 over the Lewis number. So we're going to have 1 over the Lewis number to the C power. And again, this is equal to 1. So this whole side of the equation is going to be equal to 1. So we know then if we're looking for a relationship for the mass transfer or heat transfer coefficient over the mass transfer coefficient, the right side of the equation, so we see this dAB over K. We have the same thing here, and that's going to be equal to 1 on this side, so that's going to equal 1 over the density times the heat capacity, which we're going to call the volumetric heat capacity. So if we apply that to this equation, we see that our heat transfer coefficient, over our mass transfer coefficient is actually going to be equal to our volumetric heat capacity. And this is pretty crazy considering that we have a mass transfer experiment and a heat transfer coefficient, and we can relate them via the heat transfer coefficient and the mass transfer coefficient, and that's just going to be equal to the volumetric heat capacity, and isn't going to rely on the size of your your characteristic length, your d, and it's not going to rely on your Reynolds number or your velocity of the system. And this is what is called the Lewis relation, which is very important in chemical engineering and a good thing to know. In this part, I'm going to be explaining how you can use the Lewis relation in a part of an energy balance for a wet and dry bulb temperature experiment. So with the wet and dry bulbs, you have a wet bulb, and when you swing it around when it's wrapped in a cloth, the water on the wetted bulb is actually going to evaporate, and the temperature on that bulb will read lower than that of the dry bulb because there is evaporation occurring, and the heat is supplied to the water from the air in order to cause it to evaporate, and therefore it will read a lower temperature because of the evaporation. And so I want to write out the energy balance relation between these two, relating the mass transfer to the heat flux from the air to the wet surface. And so the way we can write this is we have a mass transfer. So you have a mass transfer coefficient, and then you have a concentration difference from the surface. So you have more water at the surface compared to the air, or the concentration of the air, and so you have a mass transfer between the two. And you're going to need to supply heat to this for this to happen. So you have a heat of vaporization, and so this is your water evaporating in a mass transfer setting, and then you need the heat supplied from the air to the surface as a heat flux in order to cause this evaporation. So we can write that as a heat transfer coefficient times the difference in temperature from the air, which is going to be higher, to the temperature at the surface. So we can write that as T infinity, or the temperature of the air, minus the temperature of the surface. And so this is just the idea that you have to have like a heat source in order to heat the water in order for evaporation to occur, and therefore the wet bulb reading a temperature lower than that of the air temperature. And so we can use the idea of the Lewis relation to relate the two mass transfer coefficient and the heat transfer coefficient. And again, that relation is the heat transfer coefficient over the mass transfer coefficient is equal to the volumetric heat capacity, or the density times the heat capacity. And so we can write this out again as the heat of vaporization times the concentration difference is equal to the volumetric heat capacity, then, because we divided this over, times the temperature difference of the air and surface. And so from this, then, we can rewrite the concentrations as partial pressures divided by the gas constant times the temperature. So we can write that as the partial pressure of the water at the surface minus the partial pressure of the air in the air divided by the gas constant times temperature. And then we also know that the density is going to be equal to your total pressure over your gas constants times your temperature. So we can rewrite that as the total pressure divided by your gas constant times your temperature times your heat capacity times your temperature difference again. And so you may ask, what's this temperature? It doesn't really matter too much, but we're going to use a average temperature, so we can call this average. That's the average between the temperature in the air and the temperature of the water at the surface. And so that can cancel out, as well as the gas constant. So then you're left with the heat of vaporization times the partial pressure of the water at the surface minus the partial pressure of the water in the air. and that's going to be equal to the total pressure times the heat capacity times the temperature difference. And so ideally what we want to do with this equation is we want to derive the relative humidity. And the way we can do this is we know that the relative humidity is going to be equal to the partial pressure of the water in the air divided by the saturation partial pressure of the water at the temperature of the water. And so we know we can find our partial pressure of our water in the air throughout this equation. But you may ask, how do we find the partial pressure of the water at the surface, which is actually going to be equal to the saturation partial pressure of the water at the temperature of the water. And the way you can find this is you can use an Anton equation to find this part of the equation and then plug it into here. And then you have your partial pressure of your water in the air divided by your partial pressure of the saturation water temperature. And then you can determine your relative humidity there. Okay, so now I want to explain the adiabatic saturation temperature experiment. And I'll kind of outline the idea of the situation we have. So we have a pipe of infinite length with a flow of air throughout with the mass flow rate of we're going to call that m dot of air at some temperature, and it's going to have some degree of humidity, which we're going to display as the partial pressure of water in the air, or P1W. And that's going to flow across a stream of water at a temperature held constant at TW. And so you're going to have a outlet temperature of the air with a partial pressure of the water as well. And you're going to find that as this air is flowing across, it's going to become saturated. And so at the surface of the water, you're going to have a partial pressure that is saturated with water at TW. And so since this is at infinite length and it's going to be allowed to saturate, we can then say that the outlet stream, the partial pressure of water, is going to be equal to that saturation partial pressure of water at TW. And so what we want to do now is we want to set up a energy balance. And with this energy balance, we're going to look at the enthalpy going in and the enthalpy going out. And so the way we can write this is we have the enthalpy in, and we want to look at the enthalpy going in as a mass flow rate times the enthalpy per kilogram of air going throughout the system. And so the way we can write that is we have our mass flow rate of air going in, and we can then multiply by the enthalpy per kilogram of air. So we're going to have our heat of vaporization times our concentration of water in the air. And so the way we can write that is we're going to have our partial pressure of our water in the air over our gas constant times our temperature. And so if we say that our heat of vaporization is in joules per kilograms of water vapor, we need this part of the equation to equal kilograms, or like the moles per, or sorry, kilograms per unit volume. And so the way we can write that isn't, well, so this was going to be in moles of water per meter cubed of the air and water mixture, but we want just the amount of air or water in the air. So we can, and also we want the kilograms. So we're going to multiply by the molecular weight of the air. So therefore we would have the kilograms per mole of water, and that's going to allow us to have kilograms per meter cubed. But this is for everything, and we just want the water, as I said. So then what we can do is multiply this by the gas constant times the temperature over the total pressure. And again, we want this in kilograms, so we're going to divide by the molecular weight, or the average molecular weight of the air and water system. and this is going to give us kilograms per meter cubed. Or sorry, but it's going to be, that's if you were to take the P total divided by the gas constant times the temperature times the molecular weight average, that would give you kilograms per meter cubed, but this is going to give you meter cubed per kilogram. And that will allow you to get the mass of the air. And so then we want to add the sensible heat of the water in the air, and so that would be the heat capacity, and you're going to multiply it by the temperature going in compared to a reference temperature, but we're going to say that that reference temperature is 0, so that's just going to be multiplied by your temperature of your inlet. And so that's going to finish off the enthalpy going in, and then we can go and write the enthalpy leaving the system, or the enthalpy out, and it's going to be essentially the same thing. So we're going to have our mass flow rate of our air times our heat of vaporization, but now we have our saturated water leaving, so we're going to have the partial pressure, the saturated partial pressure of the water at the temperature of TW divided by the gas constant times temperature, and again we want this in terms of mass, so we're going to times the molecular weight of water, and then same thing, we're going to multiply by the gas constant times the temperature over the total pressure times the average molecular weight, and we're going to add our sensible heat going out, which is going to be our Cp times our temperature out, and we're going to use reference of 0 again, so we're going to just have T out. And since we're looking at a steady state system, we know that our enthalpy in is going to be equal to our enthalpy out, so we can equate these two equations, and we can see some things are going to cancel out. We know our mass flow rate is going to cancel out. We know that our gas constant times our temperature is going to cancel out. We have our heat of vaporization that we can pull out of the equation. So, and also we have our similar molecular weight and average molecular weight. So we can rewrite this as the heat of vaporization times our molecular weight of the water divided by the total pressure times the average molecular weight. And then we have our inlet partial pressure, so the amount of water in the air subtracted by the saturation partial pressure, or you can also call it P2W, whatever you want. I'm going to write it as the saturated partial pressure. And then on our other side of our equation, we're going to have our heat capacity times our temperature difference, so our T out minus our T in. And so now what I want to do is I want to rewrite the equation from the wet bulb and dry bulb temperature equation. And so we can rewrite that. I'm going to finagle it a little bit as I'm writing it down, but we have the enthalpy times the molecular weight times the partial pressure at the saturation at the water, the surface temperature, minus the partial pressure of the water going in, equal to the total pressure times the average molecular weight times the heat capacity times the temperature of 1 minus the temperature of 2. And so we have our adiabatic equation, and we also have our wet bulb equation. And so we can see that these are almost identical. And if we finagle this around a little bit, we can see that if you were to write, they're exactly equal. You would just multiply the negative sign throughout, and you would get the same thing. Move this over here, get this, and you'd have the same thing. And so what this allows us to do is to know that the temperature reading, what connects the two is that the temperature reading of the wet bulb is actually going to be exactly equal to the adiabatic saturation temperature. And so that kind of wraps everything up between the wet bulb experiment and the adiabatic saturation temperature experiment.